In question 1a, we need to describe the energy changes taking place as the bob of a simple pendulum does one complete oscillation, starting from its maximum displacement. Well, at maximum displacement, the gravitational potential energy is at a maximum, and kinetic energy is zero. Potential energy reduces to zero at the bottom of the swing, as the kinetic energy rises to a maximum. Rising at the other side, the kinetic energy changes back to gravitational potential energy. Returning to the centre, gravitational potential energy changes back to kinetic energy. Kinetic energy changing back to gravitational potential energy as the bob returns back to the start point. Throughout the swing, energy will be lost to the surroundings due to air resistance. We're then told that a young girl carries out 15 complete oscillations in 42 seconds, and in B part 1 we need to calculate the distance from the top of the chains to the centre of mass of the girl and seat. Well, for this we can use the time period as 42 seconds for 15 swings, or 2.8 seconds per swing. But the time period is also equal to 2 pi root length over gravitational field strength. Squaring both sides, we get time squared is equal to 4 pi squared L over G. Rearranging for length, we get this expression, and we can then put in the values, the time period found previously, and the gravitational field strength from the formula sheet, gives a length of the chains of 1.9 meters. In part 2, we're told the centre of mass of the girl of mass 18 kilograms was raised 250 millimeters above the lowest position. We need to find the kinetic energy as she first passed through the lowest point. Well, the kinetic energy at the lowest point will equal the potential energy at the highest point, and change in gravitational potential energy is equal to mass times gravitational field strength times change in height, which in this case is 18 kilograms times 9.81 meters per second squared times 250 millimeters, which is 0.250 meters, giving potential energy of 44 joules, and therefore the kinetic energy at the lowest point is also 44 joules. In part 3, we need to calculate the maximum speed of the girl, and this will be at the lowest point when the kinetic energy will equal the 44 joules. So we can write that kinetic energy is half mass times speed squared, and rearrange as speed is equal to the square root of 2 times the kinetic energy over the mass. Putting in the values, here I've kept the 44.1 joules that was in my calculator, rather than the 44 joules quoted here, to just two significant figures. This gives a speed of 2.2 meters per second. In part C, we need to complete this graph showing the kinetic energy variations of the girl as she passes through one complete oscillation. We can ignore any values on the vertical axis. At the start, the girl is raised to the maximum displacement, and so will be stationary and have zero kinetic energy. She'll also have zero kinetic energy halfway through the oscillation when she's raised up at the other side, and also when she returns to the start position. In between here, she'll be in the centre and will have maximum kinetic energy. Likewise here, in the centre on her return. This value could be slightly lower due to energy losses. All we need to do is join these points with a smooth curve.